You clicked on this video because you want to build a 3D Gaussian splatting project this weekend. The promise is real, but the path is far more treacherous than the hype suggests. You are about to discover why your current laptop is likely to fail before you even finish the first line of code. The narrative surrounding 3D Gaussian splatting has created a dangerous illusion. It is widely believed that this technology is a plug-and-play solution that works everywhere you install it. This belief is not just optimistic, it is fundamentally incorrect for anyone trying to move beyond a controlled demo. The reality is that successful deployment is strictly constrained by the physical limits of your graphics card. While the original research paper demonstrates stunning real-time rendering at high resolution, the underlying requirements are so demanding that they exclude the vast majority of consumer and edge hardware. The core issue lies in how the algorithm consumes memory. When you attempt to train a model using the reference implementation, the process does not just use memory, it spikes through it in massive, unpredictable waves. A pre-trained model for a standard scene can require 14 gigabytes of video random access memory just to load. This threshold immediately disqualifies most standard gaming laptops and virtually all mobile devices. You might have a powerful processor, but if your graphics card does not have enough video memory, the training process will crash your system before the optimization even completes. This limitation is not merely a software bug or a coding error. It is an architectural bottleneck rooted in the physics of data transfer. The training process generates a massive number of Gaussian primitives, which are the mathematical points that define your 3D scene. Each of these points requires constant data movement between the processor and the graphics card. Because of this, the primary bottleneck for real-time deployment is not the speed of the calculations, but the saturation of the memory bandwidth. When you try to push too many points through the connection, the data transfer queue backs up, and the rendering efficiency that made the technology famous in the first place is completely negated. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider what happens when you try to run this on a smaller device. Evidence from recent studies on memory-bounded training shows that standard implementations consume up to 80% more memory than is actually necessary. Even when developers apply aggressive compression techniques to reduce this footprint, the margin for error remains razor-thin. Successful training on constrained devices like the Nvidia Jetson AGX Xavier requires iterative pruning strategies that remove less important data points. This is not a simple setting you can toggle. It is a complex engineering challenge that demands a deep understanding of how the scene geometry interacts with your available resources. Here is the thing that most tutorials skip over. The efficiency of the rendering algorithm is irrelevant if the hardware cannot feed it data fast enough. You might have the fastest raw compute speed available, but without sufficient memory bandwidth, the system chokes. This forces a fundamental shift in how you must approach system design. You can no longer prioritize raw processing power. Instead, you must prioritize high bandwidth and sufficient video memory above all else. The gap between a working prototype and a production failure is often just the difference between a high-end workstation and a mid-range consumer card. The myth that this technology works everywhere collapses completely when you attempt to deploy it on edge devices. These devices often lack unified memory architectures, which means the processor and graphics card have separate pools of memory. This separation forces developers into a painful trade-off. You must choose between accepting a resolution below 1800 pixels or simplifying your scene to the point where it loses its visual fidelity. This reality transforms the system design from a plug-and-play experience into a rigorous exercise in hardware-constrained optimization. There is a further complication when you look at web-based implementations. Projects that attempt to bring this technology to the browser using technologies like 3.js or WebAssembly require a complete architectural pivot. They must abandon the native CUDA-based rasterization used in desktop applications and switch to a hybrid CPU and GPU rendering model. This shift often results in latency increases of 2 to 3 times. For a system that claims to be real-time, this delay is a deal-breaker. It invalidates the real-time claims on mobile devices and web browsers, forcing you to reconsider where you can actually run these scenes. So, how do you actually achieve a weekend deployment? The answer lies in abandoning the idea of on-the-fly training for your final product. Successful weekend projects rely entirely on pre-quantized files that have already been processed on high-end hardware. The true engineering effort is not in the rendering loop itself. It is in the data pipeline and the compression artifacts that ensure the file fits on your target device. You are essentially building a delivery system for a product that was manufactured elsewhere. Recent advancements in dynamic growth and pruning suggest that the window for weekend deployments is slowly expanding for edge devices. However, this expansion comes with a cost. You must accept lower scene complexity or reduced resolution. The gap in our current knowledge lies in quantifying the exact trade-off between visual fidelity and hardware cost for unbounded scenes. Most benchmarks focus on controlled datasets rather than the chaos of real-world deployment scenarios. Until we have better data on these trade-offs, the safest path remains using pre-processed assets on hardware that meets the strict memory requirements. The lesson here is clear. The algorithm is not the barrier to entry. The hardware is. If you want to succeed with 3D Gaussian splatting, you must stop looking at the code and start looking at your memory bandwidth. You must treat your graphics card not as a calculator, but as a narrow pipe that can only carry so much data at once. By respecting these physical limits, you can move from a frustrated developer facing crashes to an engineer building robust, deployable systems. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.